Assalamu alaikum. In this lecture, we will learn the difference among NFA transition graph and generalized transition graph, how the idea of state removal is being utilized to generate regular expression from the given NFA, and we will also prove NFA and regular expressions equivalence. First, to prove the difference among NFA transition graph and generalized transition graph, there is a regular expression listed on top of the slide, which is BC asterisk BC, defined over the set of alphabet containing input letters A, B, and C. The corresponding NFA, as I have drawn here, contains the input letters on the transition arrows. Whereas in transition graphs, the transition arrows can contain the strings, and strings are the combinations of the input letters. And in generalized transition graphs, we have been allowed to write the regular expressions on the transition arrows. So to prove the equivalence of NFA and generalized transition graph, to prove the equivalence of NFA and regular expression, we will be utilizing the generalized transition graph. The first part of the theorem states that we can construct NFA from the given regular expression, which has been proved here. And the second part of the theorem states that we can extract the regular expression from the given NFA. This second part we will describe by utilizing GTG, generalized transition graph, and the state removal idea of GTG, in which we will remove the states one by one from the given NFA, and at the end we will be having only the initial and the final state with only one transition arrow consisting of the complete regular expression of the NFA, which would also be the language of our machine. The idea behind state removal is whenever we want to remove the state from GTG, we have to reserve the paths being transmitted to this through this state. As in the given example, I am going to remove the state Q. Then I would list down all the paths where the state Q was already acting as a bridge. P, Q, R. Or the simple technique is list down all the paths where the state Q is being in the center. PQR is the one path, PQP is the second path, RQR is the third path, and RQP is the fourth path being transmitted through state Q. In the given NFA, we can label all of these paths as old to keep in mind that these were the paths in the old GTG, and we have to re-establish the paths in the new GTG being state Q being removed. So the new paths would be, for PQR the new path would be P2R, for PQP the new path would be P2P, for RQR the new path would be R to R after the state Q being removed. For RQP, the new path would be R to P. To remove the state, we have to keep the regular expressions intact, or we do not want to change the language of the machine. We here want to prove the equivalence of NFA and regular expression. So we want a regular expression being generated from this given NFA to be equivalent in power or accepting or expressing the same language as being accepted by our NFA. Here I would elaborate how the new paths would be established. We have to find three different paths in a single path. First is P. In case of PQR, P is the path from P to Q. Second is Q steric or loop. In case of PQR, Q steric is the loop on Q steric, which is the state being removed. Third part is the R. And in case of PQR, the third part is the transition from Q to R. P to Q, the transition symbol is E. Q steric, which is the loop on the state being removed, is G steric, self loop. And the transition from Q to R is H. So in the new path from P to R, first we have to see, is there any direct path from P to R? And there was not any direct path from P to R. So we are not taking any input letter or string in a union here, but we have a path which is passing from Q, and we want to remove the state Q. So the technique is to concatenate all of three parts in which we have divided our path. So the new path after the removal of state Q from P to R would be E, G steric, H. In case of PQP, P is P to Q, transition is of letter E. Q steric is Q steric, which is again G steric, and R is Q to P. Q to P we have a transition symbol F. So the new transition arrow from P to P would be containing a regular expression of E G steric F. The next transition was RQR. So the new path we are establishing from R to R would be R to Q, which is I, Q steric, which is G steric, loop on Q, and then Q to R transition, which is H. For RQP, to remove the state Q, P would be R to Q. The transition from R to Q is I. Q steric would be the Q steric, which is G steric, and R would be the transition from R to P. Sorry, Q to P. R would be the transition from Q to P, which is F. So if we redraw our GTG after the removal of state Q, then we only have to redraw the new paths. P to R, we have a regular expression E, G steric, H. P to P, we have a regular expression established, which is E, G steric, F. R to R, I, G steric, H. R to P, I, G steric, F. So to prove the equivalence of NFA and regular expression, we would be utilizing GTG and the idea of state removal in GTG to extract the whole regular expression from the given NFA, which would be equivalent in power. Both would be accepting the same language. Here I would be describing the example to extract regular expression from the given NFA by converting NFA to generalized transition graph and to implement the idea of state removal. On left hand side of the screen, the original NFA is being displayed, comprising of three states A, B and C. On right side, the given NFA has been normalized. The first step is the normalization of the given NFA, and this step states to introduce a new initial state labeled as init, and this initial state would be pointing towards the old initial state with the epsilon transition so that the language of NFA would not be modified. Second step of normalizing is to introduce a new accepting state and to remove the acceptance of already provided accepting state, which was C earlier, and to simply points an initial transition from C to the newly introduced accepting state. So after the introduction of new initial and new final or accepting state, the language of NFA would not be modified, as we have not introduced any input letters, but only the epsilon transitions, which would not affect the language of the NFA, but would help us to extract the regular expression at the end. We would be left only with the init state and the newly introduced accepting state, which is AC, with the single transition arrow containing the whole regular expression of the NFA. So after normalization, the first step is to remove the state A. We have to find three parts of all the paths in which the state A was acting as a bridge, and there is only one path, which is init A, B, and there is another path as well, which is init AC. Both of these paths are passing through the state being removed, which is state A. I would label these paths as old, and the new paths would be init to B and init to C. For first part, init AB, we would be finding these three parts. P would be init to A epsilon. Then Q steric would be the loop on A, and we don't have any loops, so can label it as phi steric, which is ultimately the epsilon. And epsilon in concatenation can be removed, but not in union. Our path is from A to B, which is a small letter A. So only small letter A transition arrow would remain. The next part, init AC, would be reconstructed as init to C. As we can see, there is another direct path. No, there was no any direct path. This will be the new constructed path. So for P part, we have to see the path or transition from init to A, which is epsilon, the loop on A, which is phi steric, ultimately epsilon, and epsilon would get cancelled out, or both of these are acting as a null here. Then A to C, the transition is simple B letter. So init to B, the path would be reconstructed as the input letter A, and init to C, the path would be reconstructed as input letter B in the redrawn GTG. All other paths would remain as it is. As we are only removing the state A, so we are reconstructing the paths being forwarded through state A. The next step is to remove another state, which is state B, and the only path being forwarded through state B is init B C, and the new path after the removal of state B would be init to C. Here we can see that there is also another direct path from init to C, which doesn't have involvement of any other state. Init to C with transition arrow of input letter B. We have to keep that path as well. Init to C has a direct path for input letter B. We have to keep that path as well, and the other path would be in a union. Union in regular expression can be rewritten as plus, both means or. The second path of init to C is passing through the state being removed, which is B. The idea of state removal would be same. First we have to see the path from init to B, or transition symbol from init to B, which is A. Then loop on B, which is B, so it would be the B steric. And then the transition symbol from B to C, which is A. So here we have two paths from init to C. One is of single letter B and the other is AB steric A. So both of these paths would be listed in the new GTG here. In next step, we would also remove the state C, and the simple idea to remove state would be, as there is only the single path, we can see directly from here. First, the transition from init to C, which is AB steric A plus B. Then the loop on C, which is A plus B steric, and concatenate with the transition symbol from C to AC, which is epsilon, and epsilon means nothing, empty, so we can cancel it out. So the new GTG drawn here contains the complete regular expression extracted from NFA, which we can also say that it is the language of the NFA provided, and this regular expression has the equivalence power as the NFA provided to us. Now we will move for example 2. In example 2, we have been provided with NFA comprising of 3 states, state 1, 2 and 3. First step is to normalize the NFA. I have introduced a new initial state labeled or named as state S, which is pointing as epsilon transition towards the previously highlighted initial state, which was the state 1. And I have introduced the new accepting state named as state R. I have removed the acceptance of the previously accepted states, which was state 2 and state 3 in the given NFA, and simply pointing the epsilon transitions from both of these states towards the newly introduced accepting state. This procedure of normalization would not change the language of the NFA. In the next step, I am removing the state 1. I listed down the old path in the first column of the table. Reconstructed paths have been listed down in the second column of the table. For example, the first path being passing through state 1 was S1 and 2. And to remove state 1, we have to reconstruct the path from state S to state 2. The procedure would remain the same. First, the transition from state S to state 1, which is epsilon. Then the loop on state 1, which was nothing, so the phi steric. And then the transition from state 1 to state 2, which is input letter A. Epsilon means nothing, so only the input letter would remain, which is A, in the newly constructed path from S to true. Same goes for all the paths being forwarded through state 1. After the removal of state 1, the next step is to remove state 2. The first step is to list down all the paths being forwarded through state 2 or all the paths where state 2 is acting as a bridge, and to reconstruct these paths so the regular expression would remain intact or there would not be any change in the language of the NFA. As we are proving the equivalence of NFA and regular expression, which states that the language of NFA and the regular expression would be same. To remove state 2, first I have listed down all the paths being forwarded through state 2, which was S2R, S23, 32R, 323, and the new paths reconstructed are S2R, S23, 32R, and 323 respectively. For reconstruction of path from S2R, first we have to see, is there any direct path from S2R? There was no direct path from S2R. So the next step is to see the path of S2R passing through state 2. And to reconstruct, the idea would be same. First, the transition symbol, which is taking from S2R, A, then the loop on 2. Now, on state 2, there are two kinds of loop. First is the self loop of input letter B, and the second loop on the state 2 is AA. As the first A on 2 is taking to S and the second A is taking back to state 2. So there are two kinds of loops on state 2. One is the self loop of B and the other is the loop AA. So here the loop is listed down as AA union B steric. Third part of the path to be reconstructed is the transition from 2 to R, which is epsilon. So in the automaton redrawn, the path from S to R would contain the complete regular expression listed down here. Now, to reconstruct the path from S to 3, we can see that there is a direct path from S to 3 as well, which is input letter B. So we have to preserve this path as well. Here I have listed it down as B and then taking the union of another path which is passing through state 2 of S to 3. Rule would be same. First the transition symbol from S to 2, which is input letter A. Then the loop on 2. There are two kinds of loop on 2. One is the self loop of B steric, and the second is AA. So plus AA or union AA and then whole steric. Third is the transition from 2 to 3. The transition from 2 to 3 is A, B, listed down here. So in the automaton reconstructed, S to 3 transition arrow contain the complete regular expression extracted here. Next, to redraw the path from 3 to R, as we can see that there is a direct path from 3 to R as well, which is epsilon. So first we have listed down the direct path epsilon and then union the path which is being forwarded through the state 2. Rule would be same. First the transition from 3 to 2. There are two transition from 3 to state 2. First is direct input letter A and the other is BA. On state 3, reading input letter B would take to S and then reading input letter A would take to state 2. So there are two transitions from state 3 to state 2. First is direct 3 to 2, which is input letter A, and the other is BA. So the transition from state 2 to state 3 to state 2 would be listed as a union of two transitions. One is direct A and the other is BA. Two paths have been there from state 3 to state 2. Next, the loop on state 2, which is AA union B steric, and the third part would be the path reconstructed is the transition from state 2 to state R, which is epsilon. Epsilon in concatenation can be cancelled out, but the epsilon in union cannot be cancelled out. So the new path 3 to R in the GTG redrawn would contain the complete regular expression extracted here. The next and the last path of the state 2 being removed is 3 to 3. First we'll see as there is any direct path from 3 to 3, and the answer is yes, B. First B would take from 3 to S and the next B would take from S to 3. So the direct path is there from 3 to 3, which is BB. So first we would list down BB, which was the direct path from 3 to 3. And the next we would take union with the path which was being forwarded from state 2 being removed. Rule would be same. The concatenation of 3 parts. First part is the transition from state 3 to state 2. And there are two transitions from state 3 to state 2. One is A and the other is BA. So that would appear in union. Next is the loop on state 2. Two kinds of loop. So again in union AA, union B, whole steric. Third part would be the transition from state 2 to state 3, which is AB. So that would appear in concatenation. So the path of 3 to 3 would contain the complete regular expression extracted here in the newly constructed GTG. Now, if we want to remove the state 3 as well, as we want to extract the complete regular expression from NFA, to remove state 3, first path is the direct path from S to R, which is AA union B steric. This will appear as it is, and then we have to take union with the other path which was passing from the state 3 being removed from S to R. Rule would be same. Q steric and R. P is the path from S to 3. That would appear as it is. Then Q steric would be the loop on state 3. Concatenate with the path from state 3 to R, labeled as the third path of the path reconstruction, which is R. So here we have proved that NFA and regular expression are equivalent in power by extracting the similar or the same regular expression accepting the same language as our NFA was. So by proving the equivalence of NFA, DFA and regular expression, we have proved that regular languages can be expressed as NFA, DFA or regular expression. All of these three are equivalent in power, accepting the same language. That is all. Thank you very much.